So let's get started. So today will be the last lecture from my side, as I told you on the last class, and then there'll be 4 more lectures for the diploma and for the students from Kigali on active matter, delivered by Asia Yalek. Okay, so that'll start next week. Regarding the exam for this course, it's going to be an oral exam. Probably it'll take place mid-May. I haven't fixed the dates yet, but I'll let you guys know next week, essentially. Okay. Okay. So
do we also have to take it?
Yeah, for the first part only.
No, I mean, do we have to take it the same time everyone else takes it? Because we have
no, not necessarily. No.
Okay.
We can arrange. Yeah.
Okay.
Yeah. We can arrange a different time. For sure. Yeah. Okay. So what I want to do today is try to finish up this discussion on in silico modeling of water biological systems that we started on yesterday. Try to finish up this part and then say something about hydrophobicity. So it's a bit not so smooth in terms of how I wanted to present it, but because I ran out of time, I won't be able to do it in the way that I would have liked. But anyway, it's fine. So we were discussing at the end of the last class, the different practical aspects associated with how you model liquids. And from top to bottom here, you go in increasing complexity, increasing accuracy, and increasing computational expense. And I actually forgot to add one more intermediate scale here, which is coarse grain models. Okay, so continuum dielectric mean field, coarse grain models where they are a form, they form a subset of empirical potentials, but where you don't have the explicit atoms and molecules, the atomic structure embedded. So for example, in a coarse grain model, instead of having an amino acid with all the covalent bonds, all the dihedral angles, all of it is collapsed into one atom. Okay. And so this is an approach that, of course, allows you to treat much more larger and complex systems. Then we have empirical potentials. We're going to see a bit of these different types of water models. It's basically a zoo of water models that can give you all sorts of different results, sometimes for the right reasons, sometimes for the wrong reasons. So it's important to know and be aware of these limitations. So all these things above ab initio are without electrons. Everything below here is with electrons. And so the workhorse of electronic structure is density functional theory. And over the last decade, there's been a lot of progress in understanding what's missing, even in density functional theory, for hydrogen bonded systems, which are essentially ubiquitous in biological contexts. And then finally, as we discussed at length, the nuclei in biological systems are often made up of protons. Protons are not classical particles, so quantum fluctuations, quantum effects play a big role. And so the workhorse method there is path integral, ab initio, Monte Carlo, or molecular dynamics. And I'll try to give you a flavor of the essential idea behind it. Okay, so within the empirical potentials, there are a whole range of different types of complexity of water models that you, not even water models, even in models for biological soft matter systems. It is typically very common to treat all these molecules as rigid bodies. So you freeze out the bond vibrations and the bond angles. And the reason for doing this is it allows you to use larger integration time steps when you do your molecular dynamics. And this is on the one side. On the other side, these types of fast vibrations are quantum nature anyway. So doing them with a classical empirical potential is probably not going to give you anything that's necessarily more accurate. But that's the philosophy, that's the thinking. But you'll see that flexibility, making the bonds more flexible, can change important properties, dielectric properties of the material. Okay, so those are then the flexible models, and then there are polarizable empirical potentials. So a polarizable potential is a potential where you have sites on your water molecule, for example. So in this case, this is a three-site potential. And then on top of this three-site potential, which has 3 point charges, you include polarizabilities. So and then the polarizability dotted with the electric field that comes from the environment induces a dipole on the water molecule. And so this is a way to account effectively for electronic polarization without including the electrons in there. And okay, and as you see here, there's a whole zoo of different types of water models: 3-site, 4-site, 5-site, and these all correspond to tip 3P, tip 4P, tip 5P, and essentially the community has evolved in trying to add different sites, different charges. These are of course fictitious sites in an effort to reproduce thermodynamic and dynamical properties of water. Okay, because the standard 3-site model often doesn't do the job. Okay, so this is why it's empirical, right? So over time, people have you start with this 3-site model and you say, okay, well, this doesn't work. So then you try to, like a bit of engineering, try to add different components to it, and then you hope and wait and see that it does what you would like it to do. And this is the entire biomolecular force field, let's say, community. Okay. All right. So just to give you a sense of how flexibility changes properties, I just dug out this paper that looks at surface tensions of water near an interface, and it compares how the surface tension of water near an interface changes as you add different forms of flexibility. So I want you to focus on the bottom panel. So you have an interface, which means you have a bottle of water, and you have water in coexistence with the vapor phase. And that's why, if you look in the top panel, the density goes from well, it's not exactly 1, but it goes from something bulk-like, and then the density goes to 0 because it's vapor phase, so essentially 0 density of water molecules at room temperature. Okay, and what they do is they compare how taking rigid water, so rigid water where no angle vibrations, no OH vibrations. So if you look at the dipole moment of a water molecule, it's about 2.35 dBi. Okay, that's the unit of a dipole. And if you look at the dipole in the rigid model, it's constant, right? Because there's no electronic polarization, there's no polarizability, and the bonds and the angles are rigid and are fixed. So the only way that a dipole could change without explicit polarization is if the nuclear positions change, right? Okay, because the dipole is the integral of the position into the charge. And you see that for an interface, the dipole moment looks flat. I mean, it's not really flat. Okay, it can't be. And when you include the fluctuations, which adds a type of polarization, there's a change in the dipole moment at the interface. Okay, so these subtle things, like, for example, having rigid body versus flexible interactions can change some subtle properties of things, especially at interfaces. Okay. Okay. So now you're probably wondering what these, well, I didn't say it explicitly, but all these different words here, and for sure, at some point, anyone who does molecular dynamics of some biomolecular system will encounter all these different types of water models. And so how do they do? What's if we compare their properties, just to give you a sense of that this is actually quite complicated and not in the direction that you might hope it is. So, for example, we start with SPC. It has a gas phase dipole moment of 2.27. In the liquid phase, it remains the same, and you can compute its dielectric constant from the fluctuations of the dipole, and you get 65. So the static dielectric constant of water is experimentally at the relevant temperature is about 80. And then you can see that there. Let's look at this one. This one is a form of SPC, but it has polarization. So it has something known as Drude polarization. So there's a polarizability site on the water model, and you can create an induced dipole on it because of the electric field that polarizes that. And here you see, look, gas phase 1.8, so consistent with the experiments. The liquid phase dipole 2.8, 2.9, not bad. But then you look at the dielectric constant and you get 115. So, okay, so this is not closer to reality. Let's look. The one that seems to be the closer to reality is tip 3P and tip 5P. So they're close to 80, but then they don't get the individual local polarizability correct compared to experiment. So it seems like there's no free lunch in all of this. In some cases, you will get the local polarization correct. but the macroscopic polarization, which is what the dielectric constant probes, is not correct, as in the case of, for example, this SPC FQ.
I have a question, if I may.
Yeah, sure, Alex, go ahead.
Yeah, so maybe it's something you said, but maybe so you're looking at these numbers to see how these water molecules perform, and okay.
Yeah.
And so this, I guess these different water molecules have different parameters that you have to fit at some point, no? So on what do you fit these parameters? Because
okay.
I guess it's not these numbers. Because
no, fantastic. So this is basically the huge challenge in the development of all these potentials. So basically, different models. So let me give you two explicit examples. So SPC versus SPCE. What they do is they say, I'm going to try to fit the charges and the epsilon and the sigma to reproduce the diffusion constant of water. Okay, so more accurately, SPC was developed to reproduce thermodynamic quantities first. So things like enthalpy of vaporization. Okay, so they take those enthalpies of vaporization at a series of temperatures. This is known experimentally, and then they do some fitting to get to minimize the difference between the simulation predicted enthalpy of vaporization and the experiment.
And so is there a reason for for the choice of the quantity?
What's the this is so for example, you're asking what's the choice of using the enthalpy of vaporization?
Yeah, for example.
Yeah. So for example, there the idea is you are interested in looking at when you're thinking about a liquid near an interface, like a protein or a material. The thinking is that in order to get the fluctuations that might be similar at those interfaces, the minimum thing that you need to first get right is let's say the heat you require to inject into the system to convert it into a vapor-like phase. So the idea is, if you can get this the potential to reproduce the change in the heat required to take it from the liquid to the vapor phase, then you might be you could at least have some confidence in how it behaves near another type of an interface. But I'm not saying that's correct. I'm just telling you this is the philosophy.
Okay, so there is some degree of guesswork.
Yeah. It's absolutely. This is in fact this is the message that I would like to communicate, is that okay, it's quite ad hoc. So you do it for SPC, and then you come in and you say, well, SPC does not reproduce the diffusion constant of water, correct? Aha. So now you come in and you try to tune some of the parameters to get the diffusion constant correct. Okay, so it's in this realm of the empirical developed potentials, it's been a lot of fine-tuning parameters to reproduce experimental quantities that that change over time, and actually most of the time they're done only at a specific temperature and pressure. Okay, so you don't even know if it works outside of those temperatures and pressures.
Okay.
So yeah, so you'll see shortly that there's, okay, this is not comforting at all.
Yeah, no, it's not.
And then on the other side, you might say, well, I'm a pure person. I'm going to do things from first principles, ab initio, and then you'll see shortly that even there's another zoo of problems.
Yeah.
So it's, yeah, there's no free lunch, and this is, my message is not to say, there's no value in these types of models. There is, but one should really be aware of what the underlying, theoretical error bars are, and then that guides how you can, where, in what context you can use it, and to what extent. That's, I think, that's the message. Okay.
Yeah, what bugs me a little bit is, like, for instance, that SPC, for instance, doesn't reproduce well the diffusion constants.
Yeah.
So I improve it in such a way that I reproduce the diffusion constant. But if I do this, of course, then I cannot use the model to make predictions on diffusion constant, I guess.
Agreed.
So as you improve the model, they become, maybe it's a bit naive to say, but they become more useless in the sense that you cannot make prediction because I already put everything inside.
So what I can tell you is that okay, so now let me play devil's advocate, and so okay, this is my very biased view, looking at it from the point of view of the liquid, the environment. Now, I could show you a lot of benchmarks of all different potentials like this, where they look at things like NMR chemical shifts of proteins. And if you look at the last 15 to 20 years, the ability of these force fields to converge on structural static properties is pretty okay. It's pretty okay. Where they fail, where they have a lot of challenge, and partly because people haven't really thought in that direction much, is on the fluctuations. So so for example, the model will do really well at, reasonably well at getting the if it's a two-state problem, it'll get the free energy difference correct, more or less. But the details of the curvature and the roughness of the underlying free energy, which ultimately affects the dynamics, that's a much more difficult thing to not only to validate, but also to to benchmark and to develop from first principles. Okay, so
Thanks.
there's okay. So just to add to your your doubts and your concerns. So okay, this is the melting temperature of different models. Melting temperature of water or solid ice is 273 Kelvin. Okay, take a look. SPC, 190 Kelvin. That's the temperature at which it melts. TIP 5P seem to be the better models that that seem to reproduce the melting temperature. And okay, so this again shows you that some of these models may work very well at the temperature and pressure that where they were designed to work, but if you start to move them on the phase diagram a bit, it's not clear that they're going to work. Okay, and so you'll see at the end of the lecture, basically all these challenges and problems that people faced in this community is what has inspired now the entire, world of machine learning type approaches in an effort to try to solve some of these things. But it's not, it's not easy, and it's far from a solved problem. Okay. This is the density maximum, or the density as a function of temperature. We know that water has a density maximum at 4 degrees Celsius. There's the experimental line. And if you look at these different water models within this range of where you would want to see the density maximum, it's not there. So, so some of these water models like TIP4P and TIP4P Ewald, they get the density maximum at a lower temperature. Okay, so this is not so surprising, and this is something that you see quite a bit in other contexts, that basically there's because there's an intrinsic error in your interaction potential, this can shift the phase diagram in temperature and pressure to another region. And this is important to know, because then it's fine, because you could in this model, my temperature maximum density is 4 degrees Celsius. So now I can, if I want to do something at 37 degrees or room temperature, I need to appropriately use the temperature relative to that maximum. Okay. Okay, so that's just a water alone. Now, it's an even more complicated question to ask: how do these things interface with force fields, with biological force fields? So, so the typical benchmark for tuning parameters with respect to biological systems is to compute something known as the hydration enthalpy, or free energy. So it's what is the free energy required to solvate an amino acid in your water model. So you use something like thermodynamic integration or some version of that, and you reversibly delete the amino acid from your system and compute the free energy. And okay, so this is something that's known experimentally, so you can compare with it. And okay, so the line is y equals x. In an ideal world, you'll want all these points to just sit on that line. And this is for different amino acids and different force fields. So these are just different biological force fields here. And well, sometimes it works, sometimes it doesn't. Okay, some force fields work better than others for different amino acids. And well, this is not my claim. This is the claim of the authors of this paper, which is likely because they're the developers, is that this plus Gromos 53A6, which is a type of a biological force field. Remember, it has when I refer to force field, charges plus Lennard-Jones. That's what it is. Well, and also some dihedral angles and other stuff. But those are the important parameters. And well, it's not perfect, but it could be worse. So, so this is an example of a type of benchmark that one can do in order to assess what the quality of the model is. So just to maybe summarize here a bit of this whole zoo of activity. Basically, there are different types of water models and different types of biological force field models, and the wisdom is that you should not mix different biological force fields with different water models, because these parameters, these different biological force fields have been designed with specific water models in mind. So, for example, Gromos has been tuned. So Gromos is, the made by the developers of the molecular dynamics code GROMACS. SPC has been tuned with Gromos. Amber and Charm have been tuned with TIP3P. OPLS, I think it's TIP4P. And I know there's also some more recent versions with TIP4P eWorld and TIP5P. So all the different water models have been designed to reproduce thermodynamical quantities with specific biological force fields in mind. So one has to be careful about how you combine different types of interaction potentials. Okay. Okay, and so I give you this as a last example because I think it's interesting. So there's something known as the glass transition of proteins. So just like the glass transition in glassy materials in physics, it is known that there is a temperature at which the fluctuations in a protein change drastically from something that's more in a very locally trapped harmonic potential to something that then it becomes much more enharmonic. And the idea is that this is related to the evolution of the protein and the solvent around it in a very glassy free energy landscape at very low temperatures, which then changes into something that's much less glassy. And so this has been a very
Ali, can I ask? Because I heard it before from Alessandro. He also said glassy landscape. Does it just mean a very rugged landscape, or what is a glassy landscape?
Okay, great. So glassy means very, very rugged and with very deep minima where the system can get trapped.
Okay. Thanks.
Okay, so so one of the things that has been discussed for a long time is what controls the glass transition temperature of proteins. And so people say it's because of the water, it's because of the protein, it's because of both. It's so big zoo of discussions. And so these guys here try to investigate how the glass transition temperature evolves for a protein. I forget which protein it is, but it doesn't matter, for different water models. And so basically they take a protein, they put it in a bucket of water, and they do simulations of this thing at different temperatures. This is a problem. There's a huge problem of sampling here, but let's ignore that for a second. And then they measure the mean square displacement of the water molecules and of the protein in the different water models. And just to give you a flavor here, you see that this okay, all the water models, no surprise, show some sort of transition at a particular temperature. in both the water molecule MSD and the protein MSD, but the temperature at which it occurs is different. And it shouldn't be surprising, of course, now, because, well, look at all these differences, right? In the melting temperature, where the density maximum occurs, and so forth. So, you know, one of the problems and challenges of these types of models is clearly how does its applicability and its accuracy change as I move into no man's land, essentially. You don't know, right? And that's okay. So that's a challenge. Okay, so now, well, if I was surrounded by electronic structure people, then the electronic structure people will say, yeah, but you should do first principles. Why not go to ab initio? That's correct, right? You treat you include the electronic degrees of freedom explicitly, so that's that should be more accurate than a classical potential. Aha. Okay. So let's sort of see what the story there is. Okay. So I just want to frame this in as concise a way as possible, and also because it would really require another series of lectures just to dissect, to go into ab initio MD. But so we're dealing with classical particles, so Newton's equations of motion, okay? And the forces are coming from one of the main ingredients of the potential are Lennard-Jones plus electrostatics, all pairwise interactions. Okay, this is what goes into all those force fields that I told you about. Okay, then it's a standard recipe. You've all learned this. You choose your favorite form of Verlet integration, choose your favorite thermostat, choose your favorite barostat. There are all these, you know, algorithms and arts to how you do this. Okay, so that's classical molecular dynamics. Ab initio molecular dynamics is basically the same, except for where you derive the forces. So here you take the derivative of this guy to get the forces. In ab initio, you need to get the forces from an electronic structure calculation. And so the idea is you include the electrons, choose your favorite way, density functional theory, I don't know, quantum chemistry approach, maybe it's MP2 or Hartree-Fock, it doesn't matter. Choose whatever you want. You invoke the Born-Oppenheimer approximation. Okay, so the total Schrödinger wave function of the electrons and nuclei can be partitioned into one of the electrons separately and one of the nuclei separately. And this is because of a separation in the time scales of the nuclei and electrons. So essentially, and this is known as the clamped nuclei approximation. So you can solve the electronic wave function part of the Schrödinger equation, integrating out the nuclear motion. And this works very well in the ground electronic state. Because I'm not going to get into excited electronic states because this is another beast of a problem altogether. So that's the second thing. And finally, you need to use something known as the Helm and Feynman theorem. And the Helm and Feynman theorem basically allows you to take the derivative of the energy in terms of an expectation value of the wave function, the Hamiltonian operator, and the wave function again. And so I'm not going to, you can, do the chain rule and go through this derivative, but this is where we get the forces. And those forces are then used in the same way with Verlet integration, thermostats, barometer, all that is the same. Nothing else changes. So, the main difference is in this quantity here. Now, there are some nuances, of course, depending on whether you do density functional theory or you use wave function or Gaussian basis set based approaches. The contributions of this derivative may include contributions also from the Gaussian orbitals. Okay, but okay, it's not important for our discussion today. But the only thing I want you to take away from this is that it's only the forces and how the forces are derived that are different in ab initio and classical. That's the only difference. All the other stuff is exactly the same. Okay, so no difference. And so, so one of the responses to all these challenges of all these potentials is to say, hey, why don't you do ab initio molecular dynamics? Well, okay, that's possible, and that's another field that has developed a lot in the last 15-20 years. And wait, yes. So okay, I'll go back to this, those two slides. But now let's open up another zoo of problems. And this is the density functional theory zoo. So the density functional theory, which is the workhorse of doing ab initio approaches, because that's the only theory that allows you to do, large system sizes, is an exact theory, but in practice, it's not exact. You make a lot of approximations. And the biggest approximation that one makes in density functional theory is with the choice of the exchange correlation functional. Okay, so there's this component of density functional theory, which is the exchange correlation. And, some of you might be very familiar, of course, with these different types of density functionals in electronic structure. And you see here, the black, these are the G of R's. Remember, we were discussing the radial distribution functions. So this is the quantity that people try to reproduce and check to make sure that it works. That's the black experiment. And these are radial distribution functions from different functionals. Doesn't look so good. Okay. And depending on the functional that you use, you get a very different result. Okay. So now this was how many years ago? Like 20 years ago. And well, actually, I wanted to mention something here that I forgot to mention. So how many of you are familiar with Carparinello molecular dynamics? Okay. But this is a bit of a nice historical thing. So Carparinello was developed by, okay, Jonah knows, Roberto Carr and Michele Parinello, and they developed this method, Carparinello molecular dynamics, in Trieste. 35, 40 years ago, somewhere around in the building that I'm sitting in right now. And this was a very revolutionary method. It is a type of ab initio molecular dynamics. And it, at the time, it was the method that for the first time, people were able to watch chemistry happen on a computer, because you were able to, you had the electronic degrees of freedom included in there. And so the idea behind it was, to add a fictitious dynamics associated with the electrons in something known as an extended Lagrangian formalism. And this fictitious electron dynamics then allowed you to study chemical reactions. Okay, so this is just a historical note. This was what, 40 years ago now, and that then set the beginning for then doing Born-Oppenheimer molecular dynamics. So Carparinello molecular dynamics, you are not staying on the Born-Oppenheimer surface, you stay close to it. In Born-Oppenheimer molecular dynamics, you stay exactly on the Born-Oppenheimer surface. Okay, so these are, let's say, two different methods, and now basically Carparinello is more of a legacy tool, because the Born-Oppenheimer is more accurate, and that's what people use. Okay, so this is density functional theory. Density functional theory 15 years ago said that water is overstructured. The interactions between water molecules are too strong in density functional theory, even though it's an electronic structure theory based approach. Okay, so what's missing? What's the problem? So over the last basically 15 years, what has emerged is that density functional theory in its applications misses out electron correlation. And because there's this part of density functional theory, which is the exchange correlation, and that's approximate. Okay, so there are many different types of approximations to density functional theory, and this leads to different names like BLIP, PBE, blah blah blah. Okay, and what people discovered is that the missing physics in standard DFT is dispersion, van der Waals forces. So when you include van der Waals interactions, the claim is that this reduces the structuring in the liquid. But let's look more carefully, actually. So look at this. So the label D corresponds to a dispersion correction. Okay. And when you look at this, you see, well, one of these functionals, PBE, with D3, with the dispersion correction, is still very structured. So what's going on? Okay. And PBE is a functional that's ubiquitously used in many people in the physics community. But you see, even with the dispersion corrections, it doesn't get it right. Okay, so, well, then there are all sorts of, just like in the classical potentials, you go in and you start to tune the exchange correlation. You can design a functional that will get closer to the structure factor of water. Okay, but what about other properties like dynamics? Does it work there? Oh, okay. So so this is just to show you that there are still many challenges even when you invoke the label of ab initio based approaches to studying interactions especially in biological systems, because hydrogen bonds are very difficult to get correct. And this is the source of the problem. So 80% of the interaction is electrostatics, but that other 20% is a subtle balance of all these quantum mechanical interactions, and to get it correct is hard. Okay, so this dispersion is now sort of well established as an important factor. But then, well, other people came along and they said, well, yeah, it's dispersion and exact exchange, so Hartree-Fock exchange. And so this is a paper by Roberto Carr, where they do density functional theory, ab initio, molecular dynamics, where they include dispersion corrections, they include some exact exchange, and they try to argue that when they combine, they make the temperature just right, 330 Kelvin, along with some dispersion correction and some exact exchange, they get a radial distribution function that's close to the experiment. This guy here, the dot. Okay. Well, yeah, sorry, the red line here. I think I'm colorblind, so I often mess up. It's this this line here, which is closest to the experiment. Okay. But if you look at other properties, so these are now the dipole, the dielectric properties of the liquid. So this is the dipole moment of the liquid. Depending on which setup you want to use, the dipole moment can change quite a lot. Okay, so again, this is not I'm not throwing any tomatoes at this work or at this method, but just like in choosing appropriate parameters, and just like the challenges in force fields, ab initio has its own challenges as well, and sometimes even equally challenging. Okay, if you're bored on a Friday night and you want something to read to put you to sleep, this is a nice review article that goes through many of these things and more that I've been alluding to. Now, this is the state of the field until maybe 5 years ago. This is and what has emerged now is that what's missing in the physics of most interaction potentials. So all the interaction potentials in the force field world and in density functional theory is many body interactions. So the typical approach of course, in the force field world is pairwise decomposition, right? You assume that the total interaction of all the particles can be written as a sum of pairwise interactions. Why is that true? And what has been learned now over the last 5 years is that actually this seems to be one of the the really missing ingredients in the source of many of the problems. And so there's a work now by Francesco Pesani, he's in UC San Diego, where they've spent basically the last decade or so really trying to build a model of water, and now something that interfaces with organic matter and ions and things like that, where basically the principle of the idea is the many body interaction energy of lots of particles in a system. They can be organic matter, water, whatever you want, can be written in an expansion, in a many body expansion. So single particle, 2 body, 3 body, 4 body, 5 body. Okay, and what they show and what they do is they show that by fitting the interaction energy of particles of interest, in this case, for example, water, and fitting the 2 body, the 3 body, 4 body, 5 body terms, using state-of-the-art quantum chemistry based approaches, so something known as coupled cluster. So this is the holy grail of quantum chemistry. If you do this and you fit with very complicated polynomials, so it's a very expensive model, you can get basically almost everything correct, and for the right reasons. So I think this is the real point. And I just want to show you an example. So the model is called MB-Pol. That's up here at the top. So many body polarization. And now they look at how the model behaves as a function of different areas on the phase diagram. So density. So this is the density maximum of the model. Not perfect, but not bad. Enthalpy of vaporization gets the agreement with the experiment pretty good if you look at the scale of these numbers here. This is the isothermal compressibility. So remember, we discussed that one of the anomalies of water is the compressibility minimum. And so for most liquids, the compressibility, you expect the compressibility to drop as you go below temperature and lower in temperature. And you see that this model gets that most quantitatively correct. The thermal expansion coefficient as a function of temperature, the static dielectric constant as a function of temperature, self-diffusion constant. So this is a model that gets many things right, and for the right reasons. And so this is now the approach that people are trying to take on building better biomolecular potentials and force fields, is with this many body expansion approach. And it seems to be, of course, if you it's clear that if you want to simulate a DNA or a protein or something, this is far from there yet. It's going to take probably another decade or so before it gets to a point where it can be used in those contexts. But this idea of fitting the many body interaction energies to high-level quantum chemistry approaches seems to be the missing physics in many of these, in both the classical and the DFT approaches. So, okay.
Sorry.
Yes, Jonah, go ahead.
Yeah. If I may ask, this method. So if how would you think of the idea of using using a functional that that accurately describes the local structure of water, and using the trajectories
Yes.
with another different functional that describes exactly their dipole? Does this make it better?
Yeah. This is okay. So it's an interesting idea, but you know, how do you? Okay, so if one was able to separate out the role of the functional in short range and long range interactions, okay, then you could say, yes, I'm going to build my Hamiltonian so that functional one does, I know it treats short range interactions correct, okay, and then then it gets damped out at short range, and at long range I introduce my my other functional. This idea is in fact is used in density functional theory for with they're called long range corrected density functionals.
Oh, I see.
But I think, yeah, I mean, if you so, you know, I'm still a big fan of DFT, and I'm a big fan of using it in predicting trends. But I think you know, one has to be very, very careful about because, you know, there's this sort of belief in the DFT community, in the electronic structure community, that, you know, well, once you have the name ab initio and things, it's blessed and it's perfect, and it's not true, right? You know, you can find all sorts of functionals and combination of functionals that will give you different results. But I think depending on the question, if one is interested in trends, DFT is fine. It does its job. I think what, you know, where I see a lot of potential and where people in this area are working is basically now you can now train a neural network model to reproduce the energies and forces in a model like this one that reproduces the many body energy, right? And then you don't have to do all this fancy they do a lot of fancy, you know, they use a lot of these interpolating polynomials on a grid, and it's not HPC friendly at the moment. But I think that there's a strategy where one could build on and move towards larger and more complicated systems. But at the end of the day, on the other side, the point is one still has to do, one needs a training set. And somebody has to bite the bullet on doing the training set for the biological, all the biological systems. And you know, not many people want to do that. Yeah. It's not particularly exciting. But I think that's, you know, but this is what these guys are doing. So this is exactly what, there's essentially, 20 undergraduate students, and one undergraduate is per ion, per molecule, per amino acid. I mean, this is their strategy, and well, I think it will be an enormous service to the community. But
yeah,
that's
true. Okay, thank you.
Thanks.
Then may I ask you, what does Yona mean when he says about local structure of water?
I believe this is the local structure. Right. So the idea is, so we could find some functional that works in this region.
Is it like we separate the range?
Yeah. And then we try to use something else to get the longer range part, and then also the dipole part. But it's not so, it's a delicate problem. So
yeah.
Okay, good. So this was a really, I intended it to be really a superficial overview of, just to give you a sense and to navigate you for the future on the challenges on modeling systems in aqueous environments. Okay, are there any other questions before I will say a couple of things on hydrophobicity before we close. So if the questions on any other stuff, let me know. Yes, wait, I forgot. So something I forgot to mention to you, which I in the hierarchy of models, is path integral molecular dynamics. So there's something known as Feynman path integrals, and probably, I don't know how many of you are familiar with Feynman path integrals or have heard of it? No? Okay, so basically, so Feynman path integrals was a formalism that Richard Feynman developed, and the idea is very simple, actually. So the classical partition function is integral of e to the minus beta Hamiltonian, dr dp. Okay, that's classical. But in quantum, we have operators, and so the quantum partition function is written as a trace of e to the minus beta, a Hamiltonian operator, which has the kinetic operator and the potential energy operator. And what Richard Feynman showed is that you can map, there's an exact relationship between a quantum partition function and a classical partition function. And essentially, if you want an image of this, if you have a quantum particle like a proton, so it's a wave function, and this wave function has this de Broglie wavelength, right? It has an uncertainty. You can imagine that uncertainty arising from classical particles that are connected by springs between them, and it's like a ring polymer, and the fluctuations of this ring polymer is essentially can be obtained from classical statistical mechanics. And this is essentially the idea, is that you can take the quantum partition function and make it into a classical partition function made up of p particles in a ring polymer, and then you're done, because the moment you have a classical partition function, then we do the same old classical MD, Verlet integration, thermostats, barostats, all the same. Okay, so because of this mapping of classical to quantum to classical, you can do you can build the quantum statistics from classical distributions, and so I think the diploma students have seen this maybe in the context of Monte Carlo, so path integral Monte Carlo, but the same thing exists in molecular dynamics. Okay, so that's the idea, and you know, you can then do path integral with empirical potentials, path integral with ab initio, quantum Monte Carlo, whatever you want. Okay, this is also a technique that includes then things like 0-point energy and tunneling. So the quantum effects are things that involve 0-point energy and tunneling. And so when you do this mapping of the quantum to the classical partition function, and you do a molecular dynamics of that, then you would be able to account for things like 0-point energy and tunneling. Okay, that was the only thing I wanted to mention that I didn't sort of say anything about in that list of models. Okay, let me see. Not sure. So okay, well, let's just let's just have a fun, rather than go into some details. Let's just have a little exchange on this idea. So the question is, so if you recall, hydrophobic forces are not enthalpic in origin, they're entropic in origin. They're an entropic force. And entropic forces are much more difficult to understand and disentangle, because they involve counting states. And it's difficult to find ways to count the number of states when there are collective phenomena going on. And so people have invested a lot of time in trying to distinguish, how do you, if I take a liquid and I put it near a hydrophilic surface versus a hydrophobic surface, how do I see that one is hydrophilic and one is hydrophobic? How do I know? What are the measures of hydrophilicity and hydrophobicity? Okay, so that's, and that question can be asked at a macro scale and then also at a molecular scale. And what's the difference? How do you, is what you see at a macro scale the same as what you see at a micro scale, at a molecular scale? So the standard, let's say, macro scale idea of hydrophobicity is contact angles. So, you know, you've all seen droplets of water on different types of leaves. And so, for example, if you look at a droplet of water on, they're called black kale. This is a vegetable you get here in Italy. Cavolo nero is what it is. If you look at droplets of water in Cavolo nero, they bead up. So they tend to roll up into a ball rather than wet and spread on the surface. And this measure of beading up into a ball versus spreading on the surface is measured by something known as the contact angle. So you can define a contact angle that a droplet will make with the surface, and the more hydrophobic the droplet, the larger the contact angle. This is the definition of this contact angle, assuming that it's a simple geometry. Super hydrophilic, very hydrophilic, it spreads, the contact angle is 0. Hydrophobic, contact angle is large. Okay, so that's how you measure, that's how engineers measure hydrophobic things at the macro scale. But now this is on the length scale of a centimeter, a couple of millimeters. What about at the molecular scale? Can you measure a contact angle at the molecular scale? No, because at the molecular scale, we are dealing with radial densities, GOVARs, structure factors. So how does it translate? Okay, well, it's a bit surprising and very counterintuitive. So this is a work that was published a couple of years ago, where they took different hydrophilic and hydrophobic surfaces. So the right here is hydrophilic, so it's made up of it's a surface with OH groups, hydroxyl groups, so that's hydrophilic. And then on the left here is the same surface, but with carbon trifluoride, so something hydrophobic. They measure the contact angle in the simulation. And as I told you, in the hydrophobic one, it beads up, it forms a large contact angle. And on the right, it spreads and creates a low contact angle. So from a macro scale, you argue that this is hydrophilic and this is hydrophobic. No problem. Okay, now you go in and you look and you ask, what is...
Hello, bro, please can you go to the previous slide? I want to see something.
Yeah, sure.
Okay.
Is that okay?
Yes, I'm okay.
Okay. So now let me ask you a question. If you had water near a hydrophobic surface versus a hydrophilic surface, what would you expect in the difference in this quantity? These radial densities. So if you had a hydrophilic surface versus a hydrophobic, and we looked at how does water structure near that surface, what would be the difference? Go for it, anyone.
I mean, since water is hydrophilic, if it's on a hydrophobic surface, I would expect there to be a higher radial density.
At the hydrophobic one?
Yeah, because it clusters together, right?
Okay. And at the hydrophilic, well,
it depends on at which distance, right?
Yeah, that's right. That's right. So let's say you were looking at the radial density of water with respect to the surface. So some group on the surface. And if I turn off interactions between the surface and the water, so let's say, I'll tell you my intuition, and maybe my intuition is wrong, and it is actually, my intuition is wrong, is that it near a hydrophilic surface, I would have expected stronger attractions, and I would have expected slightly larger density at the interface. But you're right that, okay, it's not just that. There's also there's.
I was thinking of the inside of the water.
Of the water, yeah.
But you were thinking about this
the layering with respect to the surface.
Yeah.
And okay, sorry, give me a second. My computer is going to die. So, and I would have expected that near a hydrophobic surface, just like there are no attractions, you expect it to be de-wetting it. It should be repelled, sort of. Okay, but this is, of course, this is not the whole story, but that's the intuition. And what's curious is if you compare, so these are the radial densities near a hydrophobic surface and near a hydrophilic surface. And frankly, it's very difficult to look at these two and say, this is hydrophobic and this is hydrophilic.
If there is no change.
There's no change. It's very similar. So even though this object here is at the contact angle level scale, it is hydrophobic, and at the contact, this is hydrophilic. So the microscopic structure of the average density is not a reporter of hydrophobicity. This is the message. So it's a bad, if you want to use this language, it's a bad order parameter. It's a bad reaction coordinate. It doesn't allow you to distinguish between something that's hydrophobic and hydrophilic. Instead, and this is, I will end with this, rather than looking at average densities, what people have discovered and learned is that what's relevant are the fluctuations. So if you look at, so imagine you took your interface, so this is your hydrophobic or hydrophilic surface in contact with water, and you were to draw a cavity or a circle, and you were to just count statistics of density fluctuations. So the number of particles that are in your probe sphere. And then in that probe sphere, you could count the variance, the fluctuations, and you could then make a distribution of those fluctuations. And this is what they do here. And what you see is that if you look at the red curve here, which is the hydrophobic surface, so the one with the larger contact angle, you see a big change in the fluctuations in the number particle density. And let me remind you that the variance of this distribution is related to the compressibility. So you can relate the number density fluctuations to the isothermal compressibility of the liquid. And so at the molecular scale, hydrophobicity is best probed by not the average densities, but by the fluctuations. And it's in the fluctuations that you see signatures of these entropic originated forces. Okay. There are many other things that I can tell you about it. I'm not going to do that, so I'll stop. Yeah, so that's it from my side for today. And as I said, next week will be another lecture, and I will let you guys know when the exam is scheduled. And then separately, of course, for the CISA students and for the diploma students. Yep. Okay. If you have questions, feel free to drop me an email, or I'm happy to chat as well.
Thank you.
Thanks.
One weekend.
Yeah, you too. Thanks.
Right.
By the way,
Ciao.
I want to ask
Yes.
the exam will cover the paper that you mentioned, or
I will not. No, it will be more less about the paper and more about concepts.
yeah.
So yeah, but it'll all be yeah, all oral. So yes.
Yeah. Thank you. Bye.
Bye, Leanne. Thanks. See you.
Sorry,
Well,
sorry.
you'll be. Well, you won't see me next week, but you'll see the other lecturer next week.
Prof,
Yeah. Yes.
can we choose to do a homework instead of oral exam?
No. This is an odd request. Why?
I don't really like oral exam.
Okay, well, it was a good time to start practicing then.
Okay. Okay.
So thanks for the question, but no.
Okay.
All right.
Yeah, can I make a request? Like, can you send me like maybe some exercises in this?
Can I send you exercises? I will do the following. I will send some exams, because in the past I used to give a written exam. Well, when it used to be pre-COVID, I will send everyone some written exams, and then yeah, you can use that if you think it's useful.
Okay.
So
Thank you, Prof.
okay. All right. Thanks, guys. See you. Have a good weekend.